So I'm going to start off with the topic, how machine learning models make predictions. So let's start off with the first slide. The first point which you need to remember is that machine learning models are able to perform because they are trained on the data. Only after a model is trained on the data, they will be able to have the inference capabilities. The inference can be anything, like whether it can be a classification or a prediction. It's completely dependent on what problem we are going to solve with the machine learning model which we have trained. And the specific topic which we are going to learn within the session is about predictions. How a machine learning model can make predictions. So the way which they do this is how it is that they are going to turn the patterns which they learn from the training, the historical patterns, into future predictions. The core concept: models are not programmed with explicit rules. They study examples, find relationships, and predict outcomes for new data. Okay, what it means is that the models are not rule based. We are not going to put any explicit logic, like we are not going to define some if else logic or while loop or anything else. They are going to understand from the data which they are trained on. They are going to find the patterns and relationships and predict the outcomes. It's completely mathematical, but it's dependent on what they learn from the data which they are trained on. What we are going to learn from in this is that basic intuition of the machine learning models to the system architecture of the machine learning models. Pattern recognition is the foundation of learning. So for this type of problem, the pattern which is being recognized is a foundation. Let's consider a human. Let's consider a human where we call it as a biological learning. So when we look at an object, we are also going to internally, subconsciously identify patterns. Even though we don't explicitly think of it, we implicitly get the patterns. Our brain identifies the patterns and finally identify what type of object is. Within this example, the human is identifying it as a cat. So it's dependent on the ears, the eyes, the fur shape, the body shape, etc. Extracting underlying patterns rather than memorizing exact images. That's what our brain does. And the same type of the same type of architecture is being implemented even in machine learning, even in artificial learning. So what actually happens is that, like for suppose there is an image where the we need to identify where we need to identify an object. Let's within here the subject is the a cat. It is going to identify based on edge detection, color values, geometry, etc. It is going to apply the learned patterns to an entirely new unseen examples. There are thousands of examples which are given, thousands of samples which are given to the model to train it to able to perform well. Algorithms require structured inputs called as features. So what these features is that, let us consider this example where the age, the salary, the temperature, number of clicks, the study hours, previous purchases, these become the features. Okay, to clearly give you an example, let us consider um, vehicle recognition. So there are multiple types of vehicles, right? A car, a bike, a truck. So the number of tires, the shape, the mileage, the number of engines, etc., the number of passengers which can fit in the vehicle, all these become the features. And the label will become the outputs which we need to recognize, like it to be a car, it to be a bike, it to be a truck, an airplane, etc. The rule. The quality of features dictates the quality of predictions. So it's all about the quality of the data which we are going to train the model on. The quality of the predictions is completely based on the data. So as we say, when it comes to machine learning, when it comes to artificial intelligence, it is all dependent on the data. The higher the quality of the data, it is easier for the for us to create a model which has a very high performance. Models translate inputs into mathematical relationships. So artificial intelligence, machine learning, artificial intelligence is completely about mathematics. It's all about representations. The inputs which we are going to pass in are going to be represented as mathematical relationships. So when we come to the topic, what we are learning in here is how a machine learning model is going to predict, right? So the core concept which is within this is regression. So regression is the most common technique in machine learning which is used for to make predictions. Y is equals to mx plus b is a type of regression where x is the input feature, y is the target prediction, m and b are the internal settings the machine is trying to perfect. So let's take an example like the number of hours studied is the input and the number of marks is the output. The training loop relies on continuous feedback. When it comes to a machine learning model, there are various steps which becomes a complete a loop till we get the desired performance. The first is the collection of the data, second is the extraction of features, third is the analysis of patterns, fourth is the calculating the error. The error is the difference between the actual output to the predicted output. Next is the adjusting the parameters. There are various different types of parameters when it comes to machine learning, like weights. So training is an iterative cyclic process, not a linear one. So it is a cyclic process which keeps on repeating till we reach a desired performance. The system repeats this loop thousands of times. The cycle only stops when predictions reach acceptable accuracy. So as we said, is the accuracy which we said till we reach that particular accuracy, we are continuously going to train the model, and we are going to fix on that accuracy, like we are going to fix on that parameters which is going to give that particular desired accuracy. Progress is measured by the reduction of errors. So, as we have talked before, error is the difference between the actual output to the predicted output. So, till we reduce this error, we are going to keep on continuously repeat the process. The objective is minimizing this gap across the entire dataset, continuous self-updating through optimization. This particular concept within machine learning is called as optimization, where we are going to reduce the error. This is also called as loss function. Different algorithms use different internal logics. There are various different types of algorithms which we can use for these predictions. Linear regression, decision trees, random forest, neural networks. These are the four different types of algorithms which are available within the slide right now. So I'm going to give an explanation on them. Linear regression is a straight line mathematical trend, like y is equals to mx plus c. The best use case for it is price forecasting, score estimation. Like for suppose you're trying to identify the price of a house, predicting the price of a house. Decision trees, cascading referrals, decision pathways. So we are going to have decisions based on like if for else cases. For example, customer behavior. For suppose if income is greater than 50K, income is less than 30K, those can become the decisions, which the conditions which based on which we are going to make the decisions. Random forest. Random forest is like a combination of multiple decision trees. Its best use case is stable, high accuracy predictions. Neural networks, interconnected layers of synthetic neurons. So it's a concept which we have in deep learning, where it is mainly used for image type of task, LLMs, etc. Like very high complex tasks, image recognition, speech recognition, image classification, object detection, etc. Gradient descent optimizes parameters step by step. Optimization algorithms governs how models improve. So as we have talked before, is the loss function, the actual output to the predicted output. Gradient descent calculates the steepness of the error curve. It adjusts parameters to mathematically walk down the mountain. So we are going to adjust the parameters as we have mentioned before. There are going to be multiple parameters which are dependent on the problem, mainly being the weights. So these are going to be adjusted such that we are going to reduce the loss function, such that the error is reduced. Step size decreases as the model approaches optimal accuracy. Models must learn patterns, not memorize data. So what models must do when they are being trained on the data is they need to learn the patterns within the data. So there are three different types of problems, like two different types of problems. One is underfitting and another is overfitting. Underfitting is the model doesn't learn the patterns within the data. Overfitting is where the model gets too adjusted to the data, so that for suppose if there is a problem, if there is a sample which is lying outside the data, like some other type of problem which needs to be solved, the model wouldn't be able to perform well on that. It can perform well on the data which it is already trained on, but not on unknown data. So underfitting, it fails to capture the pattern. Overfitting memorizes noise and errors, and generalization is the optimal place where it learns the underlying trend. So what a model need to achieve is the generalization, the ability to perform accurately on entirely new, unseen data. System performance is bottlenecked by feature quality. Garbage in, garbage out. Ignoring feature quality destroys outputs regardless of algorithm power. What it means is that the features which we are going to select for the problem needs to be high quality features. It's not about how many features we have, it's about the quality of the features and of optimal number of features. For suppose if you just consider all the different types of features which are irrelevant, then it will just lead the model to not have a good accuracy, not a good performance. So we need to select the high quality features which outrank algorithm complexity. Design error, over-engineering. Assuming complex neural networks are always superior to simple explainable models. What it means that is that we need to select the type of model, the type of technique, the type of algorithm which we are going to select should be based on the type of problem. So like for suppose, we cannot select a linear regression for image recognition. In the same way, for house prediction, like for house price prediction, there is no need to select a neural networks. We can just go forward with linear regression. So this is called as over-engineering. Selecting neural networks for a simple task like prediction, like price prediction, is not required. It is just going to make the model fail. So we need to select the type of algorithm dependent on the problem, dependent on the complexity of the problem, the type of problem which you are going to solve. So complex models require exponentially more compute and are hard to debug. So we need to select based on the type of problem which we are going to solve, based on the complexity of the problem. Production systems separate training from inference. So what it means is that, like for suppose after you train a model and you get the desired accuracy, you are going to lock in the model. So you're not going to let the model be trained again when it goes for the production. So you are going to lock in the parameters which of the model, and the model is going to be used for the inference capabilities. Like the model, we can input the model and get the outputs, but the model is not going to learn anymore because it is logged in. That's how production systems work. Raw data storage, feature storage, training compute cluster, model registering, inference API, where the parameters of the model are locked. And this API is used for the user application. So training happens offline in heavy compute environments. And after you lock into the desired performance, it will be used for the inference by locking in the training. So it doesn't train anymore when it goes for the production, when it goes for the real time. Inference happens in real time, where the user interacts with the application. Features and labels define the industry application. For suppose, like watch history plus similar users, it predicts the movies you will stream. This is in the entertainment industry, like for suppose Netflix. Cybersecurity keywords plus sender IP plus structure. This is for predicting the malicious intent, which is used for cybersecurity spam recognition. So the type of industry application which we are going to solve, the based on the type of problem, the inputs and the outputs would be different. Automotive self-driving, camera pixels plus radar plus lidar would be the input, and predicting the obstacles and lane geometry is the output. When it comes to the healthcare, patient vitals plus medical history will be the input, and predicting disease, risk, and outcomes will be the output. So dependent on the problem, dependent on the what you're trying to solve, the inputs and the outputs will be different. And the type of model which you are going to select, the algorithm for the model which you are going to select will also be different. Machine learning prediction pipeline. So the phase one is the collection of the data of where you're going to collect the historical data and the features, the input variable, and the labels, the correct historical output. Phase two, the engine. Training, the iterative learning process, how correct predictions are against the label, and you're going to make sure the engine is not overfitting or underfitting. Phase three, the output, the model, the finalized learning mathematical system, where the training of the model is logged in and it doesn't train anymore. And it will be provided an inference for the real-time capabilities. Prediction, the final model output.